Yes, we can see the screen. The stage is yours, Venks.
Okay, thank you so much, Salah, for that introduction. Hello, everyone. I'm Venks, and I'm here to talk about API design. As you see, the title of my talk is Thinking Clearly About API Design. And what I'm going to do is I'm going to share my experiences building APIs, all the way from building services to the more recent. We launched a public e-commerce API, which allows the recent launch was with a partner where if you go to the partner's website, you can actually shop on items, and those items actually come off Amazon. So we recently did build that out. So I'll share some of the learnings from that launch as well, which happened a few months back. So that's briefly about the talk. So let me get started. Before I start, I want to set some context about what I'm going to cover in API design. So the first thing is this is about service-oriented architecture and distributed systems. That's the piece I'm going to cover in API design. Keep in mind these concepts are pretty agnostic to the idea of distributed systems and SOA, but I'm going to use those examples. You can apply them to other use cases too, but the examples will be an SOA/distributed system. So that's the first piece. The second piece is I'm not going to talk about a technology, a framework, or a protocol, right? I'm purposefully going to stay away from things like REST, GraphQL, gRPC, Smithy or OpenAPI, any of those, right? I'm going to stay away from that. The idea being, I want to leave you with design. I want to talk about design. And with software design or API design, it's all about trade-offs, right? It's all about what are the trade-offs you make, right? And leave you with some thinking framework so that you can finally take that and build, internalize and figure out what tech to use and what framework or what protocol to use, right? So set some context up, right? So what's the structure of the rest of this presentation? The talk is divided into two parts. The first part is an introduction. I'll very quickly tell you what I'm covering. And then I'll talk about 7 design aspects with some examples, right? The design aspects are orientation, fluidity, purpose, mechanism, mutation, structure, versioning. So that's how this session is going to be divided. Now, let me quickly start with the introduction. So as a part of introduction, I'm going to set some context on what I mean by API, and then I'll leave you with the overall purpose, the uber purpose of an API, right? And what are the key traits of an API? So that's the first part, right? And let's jump into that. So when you have two services, in this example, service A talking to service B, when you have two services like that, what you would do is you would put an API in front of service B so that they can communicate with each other. On this specific API 8, service A talks to service B. Now, the interesting thing is they need not be two services. They can be two components. They can be libraries. They can be any two separate things. And they, these two things talking to each other is through an API. Now, what is interesting here is that the fact that you have two things, that is you have decomposed your system into two parts, A and B, service A and service B, is why you needed an API in the first place, right? So before I go to the uber purpose or the reasons why traits of an API, let me quickly talk about decomposition. So let's say you had a component A and B or a service A and B, and you decomposed it into, let's say, component A and component B, and you put an API in the front. Why did you do this, right? Why was this done? And remember, you can break it into not just two components, you can break it into hundreds of components, and you can do that iteratively. So component A can again be broken down further, and so on and so forth. But let's understand why is the decomposition done with this very specific example of two components A and B. One of the reasons you do this is to manage complexity. The way you manage complexity is the component A and B together is more complex, and when you break it down, it's easier to manage. And if you see, that is software design, right? You have a big problem, you iteratively break it down into smaller problems to handle complexity. So that's one reason why you would break it down. The second reason you would break it down is operability, because now when you have two components versus one component, you can now operate them easily. Component A and component B, you can independently operate them. You can actually form teams, if at all, to work on them, and so on and so forth. So the operability is the second reason. The third reason is changeability, right? Now, because you put an API in front of component B, what you can do is you can actually change the internals of component B. If you have a well-defined API, and we'll go into some of that towards in this talk. But if you have a well-defined API, you can actually go and change internals of component B without affecting component A, and vice versa. So that's the third reason. Fourth is reusability. Now the way the reusability comes in is you can reuse component B. You can create component A dash, and that can talk to B. So component B can be reused, as opposed to if it was one, you couldn't do that. So keep these four things in your mind: complexity, operability, changeability, and reusability, right? I'm going to go through all these four, right, with an example. Let's take an order service, right? And order service essentially is a service that manages orders, right? So I'm just making this up. Now, let's say that order service, in the earlier case, it was one service, and it had three responsibilities. The first is a CRUD operations on order. When I mean a CRUD, you create an order, you retrieve an order, you update an order, and you delete an order. So that's one piece of responsibility. The second piece you had is it also rendered an UI, right? So it's a page where you can log in and you can see your orders, right? So a quick page that kind of shows you that. And third is it had, it also gave you capability to generate reports. I've taken this example because now it's very obvious that the service is doing three things, right? And it has to be decomposed. I've taken a very simple example to just illustrate some of the concepts that I had covered previously. So if you take this example, let's say I ask you to decompose it. One of the ways you would decompose it is as follows, right? You would, a very simple thing is you would start with two services, right? Like I'm going to keep the reports aside, right? That's why I've striked that out. I'm going to keep that aside. And let's assume you had only CRUD and the web view and you want to decompose it. How do you decompose it? It goes back to the standard pattern I was talking about. So you'll have two services. You'll have an orders data store. The orders data store is fronted by an orders API. And then you have an orders web view, which is essentially the UI service, right? Or some, UI service or the piece that deals with the front end. So this is one way to decompose it, right? So let's stick to this very simple decomposition. You had one service which was doing two things. Now you've broken it down. Now let's understand how. So the four concepts I talked about earlier. Let's understand how those four are handled in this example, right? Complexity, right? Let's say the orders data store had like hundreds of fields, right? The API, you wouldn't want to expose all the fields, right? So let's say the API exposed 20 fields. You'll have lots of fields for various internal reasons, right? Like in the data store, right? You don't want to expose all of them. That's why you have the API, which is exposing the 20 most important fields that you want to expose externally, right? And the web view to the end user is showing only 10 fields. Think about this, right? So if you have some internal identifiers, they are necessary for the two services to talk, but you don't want to show them on the UI. Similarly, if you have some internal attributes that are needed for manipulation of orders, you don't want to expose them outside the orders DB. So what it's doing is it's giving you a layer of abstraction, the API, and it's helping you manage complexity by summarization. So what has happened here is that instead of the orders DB had 100 fields, we're not showing all of them. We have picked up 20, right? And then out of 20, we're showing only 10 to the end user. So there's summarization at each level, right? And this is a way to deal with complexity. Obviously, 100 fields is hard, right? 10 fields is much easier, and so on and so forth. This is one way. This is a very simple way to deal with it. So that's on complexity. The next thing we spoke about was changeability. So let's understand how changeability works. Now, let's say your orders data store was using XML as the language to store the database, or it could be any data store. Let's say you're using a relational data store to store data. Now, because you have this API in front, you can change XML to JSON and then change relational database to to something like DynamoDB fairly easily without impacting your clients. So the second piece is changeability. You got changeability there. Now the third piece is reusability and operability. So I'll give you an example of both, right? In this case, you can operate all these services independently, but on the reusability as an example, if you want to build a mobile app, right, you can use the same API, the orders API, to hook that up to the mobile app and leverage it. So you're reusing the orders DB as opposed to earlier. Now the interesting thing is you can also take it to the next level, which is in this case, if you wanted to actually build a reporting system, I would have two data stores, right? One is for dealing with low latency transactions, others for essentially bulk, right? So I'll have two data stores, so I can actually replicate and build another data store and build the reporting system separately, right? So this sort of becomes a way you kind of decompose that one system, which is doing three things to multiple pieces. So you get reusability, you get operability, right? So these are the main purpose. So I'm going to quickly summarize, right? Complexity, the way you deal with complexity is through abstractions. The APIs provide abstractions, and think about those examples where you're summarizing, right? So abstraction is showing what's most important and hiding what is not most important. So you handle complexity through abstractions. You handle changeability by hiding implementation. And you handle operability and reusability by decoupling. Now, those are three broad traits of an API. You have it gives you abstraction, it hides the implementation, and gives you decoupling. So I want all of you to keep these three things in mind. And they're also very closely related to each other, but just keep these three in mind, because as we go into the design aspects, I'll be covering some of these. I'll be touching upon these as a theme. So that's the introduction. Now let me go into the design aspects. So I'm going to cover 7 design aspects, and before I do this, I want to set context on 2 things. The first thing is I picked up 7, and these 7 are the ones I believe a lot of engineers make a lot of mistake, and there's a lot of confusion. So that's why I picked 7. There are more, but I picked 7 because I thought these 7 were the ones that were most important to cover, right? But there are more. And second is, as I go through each of these aspects, here's what I'm going to do. I'm going to introduce the aspect. I'm going to talk about some of the trade-offs, right? And then I'll leave you with a thinking framework. How do you think about orientation? Like if you have to apply this, right? So again, technology agnostic. That's how I'll flow. So as I flow into each one of them, I'm going to play it this way, right? Into these 3 themes. So with that, let's start with number 1. Number 1 is orientation. Now, what is orientation? So an API can be entity-oriented or behavior-oriented. I'll give you an example. An entity-oriented API is something like what you see on a screen, right? You have an entity. It's also called resource-oriented. You have an entity and you operate on the entity. So in this case, you have an order. You operate on the order. So you probably, if you're using something like a REST, you'll probably have order/order ID, and then you have operations on top of it, like CRUD operations, right? So that's entity-oriented. A behavior-oriented other one is also called procedural, right? And the way it works is you have a get order, put order. You can have things of that fashion. You don't operate on a resource. You have methods, right? Now, orientation is a very important concept because it's often a little confusing. But the key thing you want to understand here is this, right? In entity-oriented, you put the entity first with standardized behaviors, and in behavior-oriented, you put the behavior first. So let's understand this, right? In entity, you're saying that this is an entity called orders, and then you standardize the behaviors. The behaviors can be create, update, delete, or it can be anything else, right? You can, if you're using REST, you have standard HTTP work, but if you're not, you can put any sort of behavior, standardized behavior. So what you're saying is I have standardized behavior, but here's my entity. In behavior-oriented, what you're essentially doing is you're putting the behavior first and then the entity later. So if you see get is the behavior, order is the entity. So these are the 2 important aspects, right, of entity and behavior oriented. Now let's talk a little bit about a thinking framework. Like how, let's say you want to design an API, how would you go about it, right? Should you go entity oriented? Should you go behavior oriented? So I've got a very simple workflow. So when you start, first is think, can you model this as an entity? So use that as a choice. Let's start with that. And if you can, go ahead and do it, right? If you can't, don't force fit it. I'll give you some examples of when you can't. Or when it's not very natural to model it as an entity-oriented. Because when there are lots of behaviors can't be standardized. It becomes hard to model something as an entity-oriented. Take the example of, let's say, a preview order and a create order. So we have this real example in our e-commerce API where you have 2 orders, and you create, preview, create, and confirm. And some these are they're not natural. You don't have standardized. You have lots of behaviors, and they're different. Send message, receive message. Shut down, reboot. All of these are probably better modeled behavior oriented. You can also model them entity oriented, but it's just harder. It's tricky. So if you can model something as entity oriented, go for it. If you can't, then go take the behavior approaches. If you and often you'll find that you need to use both. So you go hybrid, try to limit it, but across API, if you can standardize it to one, either an entity or a behavior, you're better off rather than doing both. So keep that aspect in mind. Limit hybrid as an option. So that's your thinking framework on orientation. with that, let me go to the second design aspect, which is fluidity. And this is also my favorite topic. So let's take fluidity with an example. Let's say you have the get order API, and all this API does is you'll get the order details. You pass an order ID, it'll give you the order details, right? Now, when I talk about fluidity, I'm essentially talking about a spectrum. When I mean a spectrum, get order API could have been designed like, to one end of the spectrum, like in the example where you have a get digital order, get physical order. So for each type of order, you have an API. Okay, so you could have built it that way, or you could have built it get order and the type is passed as an input. Or you could go to the other end of the spectrum where you just have an API. The name of the API is just e-commerce, right? And you pass, the type of the API order as an input, right? So you have this spectrum of things that you can do. It's not like get order is probably in the middle, but you have this end of the spectrum. So it's also called on the, as you move towards the left, it's called fine grained, and as you move towards the right, it's called coarse grained. It's also called specific versus generic, and so on and so forth. Now, how do you know? Okay, now the important piece here is how do you know what is right? Okay, and that's where design comes in, and that's where one of the things I'll recommend is in AM Tech 2020 I did a talk with a very similar title. It's called Thinking Clearly About Software Design, and look at the abstractions part of it. I've put a link here, and that and I talk about how to arrive at the right level of abstraction in design in general, and you can apply a lot of that here. But as a part of this talk, I want to specifically talk about why fluidity impacts an API design. Okay. So let me take an example, right? Throttling by default, throttling is applied by API. So most of the framework, more often than not, throttling runs on an API. You throttle by an API, right? Like you said, okay, this API, this is how you throttle this client. You design throttlings by that. You design metrics by API. You design access control by API, and you design timeouts by API. So imagine, right? Like, so as you go more coarse grained, some of these that are usually done at an API level, right, becomes trickier for you because you're very coarse. As you go fine grained, you get a lot more of these fine grained metrics, right? I just want to keep this in mind. Not that this is the only design trade-off, but these are important trade-offs to consider. Now, I want to dive into a specific piece, which is timeouts. Timeouts. So for those who don't have context, I'll give you some context. So this is a service that I show. The service has some clients and dependencies. A typical service. So what the service does is a client calls and it does some work, and then it calls a dependency, gets some response, does some piece, and gives it gives an output. And in this case, I've drawn two lines, and the service has two threads. Okay, simple. It's a simple service. You can use any language, but let's keep it Java. It's a Java-based service. It has only two threads, which means it can handle only two requests at any point in time. And it has a bunch of dependencies. Now, how do you calculate the TPS of this service? When I mean TPS, transactions per second. So if you use Little's law, TPS is nothing but the number of threads by latency. Okay, let me explain this as an intuitive example. Now, in this case, you have two threads, and let's say the latency. When I mean each thread is, approximately 1 second. It takes 1 second, right? So you have two threads. Each thread takes 1 second. So the TPS is 2 by 1, which is 2. What it means is that the service can at most handle 2 transactions per second. Let's try to intuitively reason about it, right? You have two threads. At time t0, two requests come. Both the threads are handling it. So it cannot handle any more requests. So if you, at time t0, if a third request comes, it probably has to wait or run around. So it's handling two requests. Now, at time t1, because each request takes 1 second, that's the latency, they finish at time t1, and it can handle 2 more requests. So it kind of goes on this way. So TPS, the max TPS, the upper bound TPS in this case is 2 by 1. Obviously, if the latency varies, the TPS varies, right? But in practice, the key thing to write is latency is not fixed, right? Like the latency of each thread depends on the latency of a dependency because it's waiting. If you have, I'm assuming you have a threaded application, so it's waiting on your dependency and the work it does, right? So that's where it is. Usually, the wait on dependency is usually higher than the work it does. So I'm going to just assume that for all practical purpose, the latency is the latency of the dependency, right? Like just for the for purpose of understanding. But usually there's something more that it depends on the type of service. So with that, what we do, right? Like, so we say latency of your dependency is again not predictable, right? Like the latency of the dependency goes up and down. You have like percentile numbers they publish. Now, how do you figure out what the right latency is? Now, usually what you do is you try to get a lower bound TPS. And the way you get a lower bound TPS is you try to put latency as a timeout, right? So whenever you have a dependency call, you set a timeout. Now, the reason you set a timeout is because of the latency, it's a circuit breaker, right? Timeout is a circuit breaker. If the dependency does not respond, you error out and free up the thread. So in this case, the lower bound TPS is essentially, if you replace latency with a timeout, you get a lower bound TPS because timeout. Let's understand a little bit about what happens with timeouts, right? Let's say you do not set a timeout, okay? This causes a brownout, and let's reason about it, right? It's because 2 by infinity is a brownout, and the way you reason about it, if you have 2 threads, 2 requests come and the dependency is not responding, and you don't set a timeout, the threads keep waiting infinitely. So your service has 0 TPS because it's not doing anything. If you set a high timeout, it reduces the TPS. See the example here, right? You have 2 threads. Earlier, the timeout, let's say, was 1 second. You get a TPS, lower bound TPS of 2. And let's say you set the timeout as 20 seconds. You get the TPS of a single host has actually gone down to 0.1. Now, I want you to keep both of these in mind, right? The 2 extremes, right? Not setting a timeout and setting a very high timeout. And setting a low timeout has other problems, but I will not cover that. But fundamentally, timeouts usually are set by APIs. So if you have your clients, they set timeouts by APIs. They don't set so APIs with varying timeout will make it hard for you to scale a service. So keep that in mind. So if you have more coarse-grained APIs, as the example that I gave you, it has varying timeouts. So now it's going to be very hard for your clients to set timeouts. If you have very fine-grained, timeouts become easier. So that's a trade-off that you want to make. But in general, the fluidity is about getting the abstractions right. With that, let me go on to the third piece, which is purpose. The third design aspect. Now, the purpose is asking essentially 3 things. First is, who is your customer? Now, the customer can be an end user, can be a developer, or it could be an integrator. So depending on these 3, your API design criteria change. The next is, what is the use? Is the use, for example, between 2 services? Is the use between 2 networking devices? Because that varies, right? Do you want to use binary versus what are the trade-offs there, right? Then the most important piece is access pattern. The access pattern makes a big difference. Now the question is, if you look at the get order API, that was giving you a get order by an order ID, right? So it's a pointed query. You can have an API that says get last 10 orders. Now the latency and all of it will be very different from a pointed get order. Similarly, if I say get all orders for a customer versus get all orders for a seller, these APIs are different. The question is that depending on the access pattern, you want to, these 3 parameters define a purpose and define the API design criteria. With that, let me move on to the 4th aspect, which is the mechanism. Now, I'm going to cover 4 mechanisms and briefly go on. One is sync. A sync is essentially a request and a response. So you get a request, you get a response back, right? And that's a sync. Example is the get order ID. So you pass the order ID, you get a response back. That's a synchronous API. In an asynchronous API, the response is not immediate. Now, the example is a get a report or generate a report, right? A generated report takes time, depends on the time frame. Like if you want a report for a year, it will take longer than if you want a report for a day. So in async, the response is not immediate. Now, how do you deal with async? Now, there are essentially 4 ways to deal with it, but one is you just wait. You treat the async as a sync request and wait. You could do that, is wasted resource, but you could do that. The second way to deal with it is polling. Which is what you do is you have 3 APIs like I have shown, which is you submit a report, and then you check whether the report is generated. You get a request ID back, and then you use the request ID to query if the report is generated. And if once the report is generated, you download the report, again, based on the request ID, right? So you have like 3 APIs. So what you have done is you've changed the async to a sync, right? To 3 sync APIs and essentially put polling in place. So that's the second way. The third way is you can use something like callback/push, where you say you submit the report and you give a callback URL. You can also give a callback queue. A lot of other things. Fundamentally, you get a callback URL, And once the report is done, a URL is called back, and you can use that. Now, all these three approaches, right, are essentially build your own, right? And they use sort of a synchronous mechanism. You can also use a protocol/framework that kind of gives you some of these streaming APIs and callback mechanism. You can use that, but that's the second piece in earthing. And you want to choose one depending on various parameters. Definitely modeling things like modeling earthing things like callbacks. Polling is very easy to scale, but it does have some wasted resources. So you want to figure out what works best and use that. Definitely waiting will is not the best in terms of performance efficient. So those are the two mechanisms, sync earthing. We also have one which is bulk. Bulk is essentially transferring a lot of data. You could use streaming, or you could APIs to kind of do that. The other piece is messaging. In a messaging, you have a producer, consumer, and a queue. So the producer passes message to a queue, and a consumer downloads message from a queue. So that's how this works. And the way you have distributed queues. Examples are SQS, SNS, Kafka. You have lots of options. And key thing to remember here is that you will have out of order in a distributed system. Guaranteeing order is hard. Not that it's impossible. It's extremely hard and it's expensive. And doing exactly one is hard. So keep these two design criteria in mind when you talk about messaging. So that's with messaging. So now we go towards the fifth piece, which is essentially mutation. When I mean mutation, the thing is mutability. So make your APIs immutable, which means if you get the same inputs, you get the same output. So try to internalize this. You pass the same inputs, you always get the same output back. Now, why mutation? Mutation makes it easier to reason about, right? It's very easy to reason about. It makes, if you go back to the earlier example of out-of-order retries, right? It makes it safe to retry. You can retry the calls and you're fine. There's no side effects. And it gives you performance benefit now because you can cache the response and store it, so you get the performance benefit out. So those are the three reasons you should do mutation. So a thinking framework for mutation would be something like this. When you're starting, if your dependencies are idempotent, right, your job is done. So make things immutable. That's your first choice. If your idempotent dependencies, you have to be really bad. You have to do really bad things to make your API idempotent, right? If your dependencies are idempotent, you're pretty much good, right? But let's say if the dependency was not idempotent. Example is a get order, right? And a get order with an order ID, the data for order changes. So if order was shipped, the status changed to ship. The order was canceled, it changes to cancel. So get order is not idempotent. So what do you do then? Then one of the things you can do is you can cache the response. And great. So when you cache the response, whatever the input was given, you cache the response. But in this case, to the get order API, you're actually passing an order ID. Now, so you can't cache by order ID, right? Because the order is mutating. What you do in this case is that if you don't have a unique key to cache by, you use something called an idempotency key. You can pass an idempotency key. It could be a request ID, and you can cache by the request ID. So you can pass it. So that's one way to make your ID. So this thinking framework is essentially allowing you to make your API idempotent. So again, to summarize, you start, if your dependency idempotent, you're good. If they're not, see if you can cache. If there's it gives you a request ID type that you can cache. If you cannot cache, what you do is you ask for an idempotency key. Now that's one part, right? But what if your API was mutating? Okay, is mutating. So let me give you an example, right? In the case of a get orders API, the order is mutating. It's changing. Order state is changing. Order can have multiple shipments, and one order can be partially canceled. So it's mutating. What do you have? Fundamentally, something is mutating. How do you represent it, right? While making things immutable is great, but when you have fundamentally things that are functionally mutating, what do you do? There are a few things you can do. The first thing you can do is you can actually return a history. So what a history is essentially, if you is a set of transactions that you can return where you have you give a snapshot, right? You say, okay, this is the latest. Give a pointer to the latest and give all the previous records, right? So whenever you do that, whenever you call the API, you give the latest. So that way, it does not matter when the caller called you; they always get the history, and they know that the API, fundamentally is changing in nature. That's one way to do it. But obviously, that makes your API more expensive. So if you have a lot of changes, you'll probably return a lot of data. So to optimize that, what you can do is you can give different APIs. So in this case, get latest order gives you always the latest order. Get order history will give you the history. So that can be a more less. If you have a latency sensitive use case, like in the UI, you just want to show the latest order, you kind of go do that. But if you want a history for whatever operations, you call the more little higher latency API. So that's your thinking framework on an API that's mutating. With this, let me go on to the next piece, which is the structure. What I mean by structure are essentially three things. First is what I want to structure is what the input to your API is and what the output from your API is. Keep your structure finite. Keep it homogeneous and keep it predictable. When I mean homogeneous, if it's a list, let it be a list of the same things. The reason is if you have a list with a string with an integer and all of that, it's super hard to write code to handle it. It becomes it becomes hard to reason about. Keep things finite and predictable, because end of the day, you have a developer who's writing code against your API call. So you want to make it easier. So keeping it finite, homogeneous, and predictable will make it easier for you. One of the key pieces that I want to cover with respect to structure is about notifications. When I mean notifications, I'm talking about queues. And the recommendation here is keep your notifications lightweight. When I mean lightweight, what you pass to a notification, keep it small, right? Like don't pass a lot of data. Keep it immutable and keep it simple. Okay, when you pass messages to the queue. And let's see why. First is size, right? If you look at most of these distributed, queuing systems, they have limit on the size. So, if you start passing data, at some point you'll hit a limit. But most of them have reasonable limits, but keep that in mind. The second piece is ordering is hard. We just spoke about it, right? Ordering is hard. And if you're actually passing data, and think about it, right? You're passing data and, you get data in different orders. It's super hard for the consumer to, take that and operate on it, right? Because the data is now no longer used. Rather, if you pass things immutable, if you go back, I said keep things small, immutable, and simple, right? If you just pass, let's say, a query parameter, if you just say that, hey, something has changed in the order, here's the order ID. They can always, it doesn't matter when the notification came, they can actually query and get it back. So that's the piece on ordering. The other thing is on change handling, right? Like now, if you're passing your complex data on a notification, and if you change it, it's going to be extremely hard to pass that on, right, to the end client. Whereas with APIs, you can do interesting things, and we'll talk about change in the second thing. But one of the important pieces I want to talk about is the idea of a poison pill. Now, what is the poison pill? When you have a queue, in this case, when I have a queue, and what I've shown here are two messages. The third one is stuck. When I mean stuck, what I mean is that I'm trying to retrieve the message. So usually what happens, you have a distributed queue, you have a producer who will produce the message, and you have a consumer consuming the message. Typically what happens, the consumer consumes the message and does some processing and acknowledges back to the queue saying that I've consumed the message. This is what happens. Now, when you're consuming from the queue and you are unable to process it for whatever reason, it could be a bug in the code or you're doing something and it errored out, you will not do that acknowledgement back, which means that message is stuck in the queue. It gets there's an attempted DQ, but it does not get an acknowledgement. So that cycle continues for a while, and finally, most queuing systems will take that message and put it to a dead letter queue. And that DLQ is, it takes it off so that the poison pill does not take away all your thing. And once it's in the DLQ, you realize that it's sitting there, and you have to manually clean it up. Now, imagine if you had data or complex things in the DLQ, it's completely unhelpful, right? If you're passing data, and this is the only primary mechanism, it's sitting there till someone manually comes and cleans it up. So these are the reasons, fundamentally, you want to keep notification lightweight. The next thing I want to talk about is versioning and change management. Versioning is a way to manage your changes. Now, when I mean manage your changes, what I mean is something is changing in your API, right? And that's how you manage it. Now, with APIs, it's a tricky trade-off, right? I'll give you an example. Let's say I have orders V1 and V2, right? You can obviously, when things change, you can put a version there on the name. But if between order V1 and 2, the challenge with versioning with APIs is I don't know what has changed. I don't know what to reason about, right? I'm now writing if conditions in my code for version 1, version 2. I don't know what they are. It becomes hard to reason about. So with versioning, before I go to the thinking framework, I want to explain what are the kinds of changes you'll have, right? So let's try to understand that, and I'll leave you with the thinking framework on versioning. So on versioning, you can, the three things can change. The first one is a type. When I mean a type, earlier, let's say URL, it was a string. Now you put a URL to a domain data type, right? So that's one change that you can have. Now, when this change happens, it's fine, but and this is one change that will happen. You'll have to figure out a way to deal with it, right? So this type is one type of change that can happen. The second thing is a structure. Let's think about it this way. You had a flat structure for an order. You realize that it has to be, you have to put some more hierarchy internal, and you realize that you put a wrong structure and this is the right structure, or the structure has evolved, right? So that's one way to change it. So structure can change. And the third thing that can change is data. So if I go to data, I want to go back to the order example. And if you see in the earlier example, the order was mutating. So fundamentally, the data was changing. Now, you have three reasons to change. Now, if you use order V1 versus order V2, I don't know what has changed. And so let's leave with the thinking framework. What do you do? Like, do you just go blindly put version 1, version 2, or do you do something else? Now, a thinking framework that I'll recommend is this, right? So when you have three types of changes, type, structure, or data, the first thing you figure out is this a new concept? Like the type has changed. Should it be a part of this API, or should it be a different API? Structure is completely changed. Is it even, are you overloading an API? I mean, are you changing the fluidity and overloading the API, or data? So the first thing you think through is it a new concept? So, and this is not easy to reason about and do, because whether it's a new concept or not is a little tricky, right? Because sometimes it's not obvious at the first glance. It takes a lot of iteration, takes a lot of thinking to understand if something is a new concept should be added. Now, if it is a new concept, yes, then go build that new API out. Or if it's not a new concept, then think about, is this a correct API, or is there an existing API that you have? So that's the piece. Now, if you rule these two out, right, at that point, two things, right? First is see if you can make the change backward compatible. At that point, you don't need a version. If you can make a change backward compatible, you don't need a version, but that's a trade-off you'll have to make, because take the example of the URL, right? A string versus a domain, you will probably have to pass both the data, and now you're duplicating data, increasing the size. So it's a trade-off. But if you can make it backward compatible, if not, use the other option of a change history I talked about. You give a change history, right? That may work for data. That may also work for structures. So you pass both the structures, right? So you're essentially duplicating. See if you can do these. If you can't, as a last resort, go put a version label. But use this as a thinking framework, because putting a version is often very easy to do, and you keep bumping things up, right? But that is where your API starts to rot. So you want to think through that and figure that out. So with that, I'll go into I'm pretty much towards the end of this talk, which is left you with essentially 7 design aspects. Again, there are many more. So keep these in mind: orientation, fluidity, purpose, mechanism, mutation.